So in the last session, we established a necessary and sufficient condition for two algebraic elements to be conjugates. And the result is that if alpha and beta are algebraic over a field F, then alpha and beta are conjugates over F if and only if the map psi alpha beta from f of alpha to f of beta defined by psi of alpha beta of C0 plus C1 alpha plus dash dash Cn alpha n is equal to C0 plus C1 beta plus dash dash Cn and minus 1 and minus 1 and minus 1 beta and minus 1 is an isomorphism. Where the degree of alpha over f is equal to n. This is definitely a map from f alpha to f beta, but when it becomes an isomorphism, then alpha and beta are conjugates. And when alpha and beta are conjugates, then this is an isomorphism. That's what we proved the last session. Want to go over with some of the properties of this isomorphism. By the way, this isomorphism is called conjugate isomorphism. Conjugate isomorphism. Called conjugate isomorphism. There are something which we want to note in this conjugate isomorphism. First of all, when we say alpha and beta are algebraic, over F, what does that mean? This means that alpha and beta belongs to the closure of F. The closure of F is the algebraically closed extension of F. So any elements which are algebraic over F has to be in here, in F closure. It's a closure of F that is algebraically closed. So when you say alpha and beta are algebraic over F, it automatically means that both of them belongs to the closure of F. One property that we need to observe here of this conjugate isomorphism is these elements C0, C1, C2, etc. These are all coming from F. So this is the if you draw a diagram, this is our F and this is our F closure. F closure contains all the algebraic elements, all the elements that are algebraic to F. It's algebraically closed. Or in other words, any polynomial over f of x has a 0 in F closure. So this alpha and beta, it could be here, but if it's inside F, it is of no interest. So it is actually inside F closure, somewhere here, or probably here, no problem. It's also algebraic. And if these C0s, Ci's, all Ci's are coming from here, inside F. All Ci's are coming from inside F. It doesn't go beyond F, all Ci's. So, if you take an element from F, let C belongs to F. It's actually this isomorphism, conjugate isomorphism is a map from F alpha to F beta. That is, this is our F alpha. And this probably, there is another one. This is not going to be like this, but for now, let's assume that this is F beta. This is F alpha. So you are mapping from this field to this field. Both are extensions of F. So it is actually, if you draw in a different way, it will be F of alpha, F of beta, and this is our psi of alpha beta, and there is an F here, and there is an F here. These both F's are same, but if you want to do it, if you want to draw it outside, then this is how the picture is going to be. So I'm going to take an element from here, C. So where is the image of C in FB, F of B, under psi of beta? So psi of alpha beta of C, what is C here? C is actually, you don't have any terms here. You only have C0, and that C0 is C. C1s, etc. up to Cn minus 1, all are zeros. There is no alpha terms here, because all the elements are coming from C. So this is going to be C, because if you take out all these elements, and if you take out all these elements, psi of alpha beta of C0 is equal to C0, and that is exactly what this one is. What does that mean? This isomorphism, this conjugate isomorphism, leaves the field F fixed. That means this conjugate isomorphism from F of alpha to F of beta leaves F fixed. Meaning, for any element of F, it is an identity map. So in other words, you can say psi of alpha beta restricted to F is the identity map. If it is restricted to F, it is an identity map. Okay? That is one property of conjugate isomorphism. Conjugate isomorphism leaves the base field unaltered. It won't alter any fields there. Another important property is that psi of alpha beta of alpha, what is that? Meaning you don't have C0 and you don't have anything after C1, and C1 is 1. So this is going to be, the map is going to be beta. What does that mean? That means the psi alpha beta, that is conjugate isomorphism, maps a algebraic element or an element an algebraic element to its conjugate. Always. In fact, if you consider an element within F, C is so the conjugate of C is itself. So every algebraic element algebraic to F maps to its conjugate. So there are two important properties of conjugate isomorphism. One is it leaves the base field fixed. There is no alteration there. You are mapping to itself. This is an identity map over F. And any algebraic element, an element of an algebraic over F is mapped to its conjugate. Now we are going to take a look at the conjugate isomorphism in a different way. Actually, we are going to characterize the conjugate isomorphism. So let us assume that F is a field and there is a closure here and there is an algebraic element. So let alpha be algebraic over F. Now, I'm going to define a map, an isomorphism. Let psi be an isomorphism from F alpha, because F alpha is a finite extension of F, to a subfield of F closure fixing F or leaving F fixed. Meaning there is a simple extension here. This is F alpha. This map is from F alpha to another subfield of F closure. And it is a isomorphism fixing F. Meaning for all A in F, psi of A is equal to A. That is the meaning of fixing F or leaving F fixed. I didn't even say that this is a conjugate isomorphism, but we are coming there. The property of this isomorphism is only like this. There is an algebraic element and this isomorphism is from the simple extension to a subfield of F, fixing F. Okay. Now, alpha is algebraic over F implies there exists an n such that degree of alpha over F is equal to n. And there exists a polynomial p of x a0 plus a1x plus dash dash an x to the power of n belongs to f of x such that P of alpha is equal to 0. But psi is an isomorphism. So let us compute psi of P of alpha. See, this P of alpha is definitely in f of alpha. Actually, this is 0. Psi of 0 equals, because this is 0. And that is equal to, you can expand this, psi of a0 plus a1 alpha plus dash dash an alpha to the power of n. And because this is an isomorphism, we can write it as psi of a0 plus psi of a1 times psi of alpha plus dash dash psi of an psi of alpha to the power of n. And that is equal to, see, it also says that it's fixing f. All these ai's are from f. You can say ai's from f. So psi of a0 is a0. Psi of a1 is a1. Then we'll write it as psi of alpha plus dash 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 an psi of alpha to the power of n. We can take this n out because it's a isomorphism. And that is equal to 0, because isomorphism maps 0 to 0. So what is this? This is actually psi of P of psi of alpha. Sorry, not psi of. This is just P of psi of alpha is equal to 0. In other words, psi of alpha is a 0 of P of x. What is P of x? P of x is the irreducible polynomial of alpha. So that implies alpha and psi of alpha are algebraic and their irreducible polynomials are same. Meaning the irreducible polynomial of alpha over f is equal to irreducible polynomial of psi of alpha comma f. And that means alpha and psi of alpha are conjugates. So if you take an isomorphism from the simple extension to a subfield of f, fixing f, then that will become a conjugate isomorphism. Meaning it is going to map every algebraic element to its conjugate. And of course, this subfield is going to be then the subfield that is then the image of psi is f of psi alpha. It's a simple extension of the conjugate of f. Now let us assume alpha be algebraic over F. So alpha can have more than one conjugates. So for each conjugate beta of alpha, there exists a unique isomorphism psi of alpha comma beta from f of alpha to a subfield of F closure satisfying the following properties. The first property is psi alpha beta leaves F fixed, and that implies alpha beta of A is equal to A for all A in F. Second property is it is really mapping alpha to beta. This result follows directly from the proof of existence of conjugate isomorphism. In the conjugate isomorphism, what we proved is for two elements, algebraic elements that are conjugate, there exists a unique isomorphism, and that we call it as conjugate isomorphism. And that isomorphism is the one which we are talking about here. So here actually B is equal to conjugate of alpha. And the uniqueness of this isomorphism comes from the definition of the isomorphism. Meaning the isomorphism depends only on F and alpha. So it is unique. So we are going to combine those two results together. So let alpha be algebraic over F. Then the first result is every isomorphism from F alpha to a subfield of F closure leaving F fixed alpha to a conjugate of alpha. That is the first result. Conversely, for each conjugate of alpha, there exists an isomorphism from F alpha to a subfield of F closure, fixing that or leaving F fixed and maps alpha to beta. For each conjugate al beta of alpha. So here it says that every isomorphism from F alpha to a subfield of F closure, leaving F fixed, maps alpha to its conjugate. So you are not taking any isomorphism, you are taking an isomorphism that leaves F fixed from F alpha to a subfield of F. If that isomorphism fixes F, then alpha maps to the conjugate alpha. The second result says that for each conjugate of alpha, a beta of alpha, then there exists a isomorphism from F alpha to a subfield of F closure, leaving F fixed and maps alpha to beta. Now let us do some examples on conjugate isomorphisms. Root 2 is algebraic over F or Q. And the conjugate of root 2 is minus root. So we can always think about a conjugate isomorphism, that is psi of root 2 comma minus root 2, that is from q of root 2 to q of minus root 2. And what are the elements of q root 2? Q root 2 is equal to a plus b root 2 such that a and b are rational numbers. Because the irreducible polynomial of root 2 is of degree 2, x square minus 2. So the simple extension has to be like this. So what is xc of minus root 2 is equal to a plus b times minus 2. So you can have minus root 2, a comma b. So what is the definition of psi of root 2 comma minus root 2? You take an element from here. This is a general element of here, and that will be equal to, this is C0 and this is C1. C0 actually is same as A, and this is going to be the conjugate of this. So this is going to be B, actually plus B times minus root 2. Minus root 2 is the conjugate of root 2. do some examples, and then some of little more complex examples than this. Let us consider a field Q of root 2 comma root 3 comma root 5. Let it be E. And let us take C of root 2 comma minus root 2 from, not from Q. See, this is actually equal to, you can write it this one as Q of root 2 comma root 3 of root 5. Or you can write it as Q of root 3 comma root 5 of root 2. Or you can write it as Q of root 5 comma root 2 of root 3. All are same. This we are going to define from Q of root 3 comma root 5 of root 2 to Q of root 3 comma root 5 of Q of minus root. Because root 2 is not inside here, so this is as good as saying Q of root 2. And Q root 2 is algebraic over Q of root 3 plus root 5. No problem. With the same irreducible polynomial. Similarly, we are going to define psi of root 3 comma root minus root 3 from Q of root 5 comma root 3 of root 2 of root 3 to Q of root 5 comma root 2 of minus root 3. Similarly, psi of root 5 comma minus root 5 from Q of root 2 comma root 3 of root 5 to Q of root 2 comma root 3 of minus root 5. Now let us compute. So these are the definitions. Let's compute, for example, psi of root 3 comma minus root 3 of psi of root 2 comma minus root 2 of root 3 plus root 5. Or probably you can say 2 root 5 to make it little bit more complex. So how do you define? See, what is the definition here actually? The definition here is going to be psi of root 2 comma minus root 2 of a plus b root 2 is equal to a minus b root 2. But this a and b are not from Q. This a and b are Q of root 3 comma root 5. So similarly, I am not going to say everything here, but this is what is going to be. The difference is only the scalars. The scalars are coming from, not from Q, but from this. So here, this is equal to psi of root 3 comma root 5, sorry, root 3 of, what is this? If you have a root 2 inside here, then it has got an effect. Otherwise, it is same. We are not changing. See, we are actually fixed. When you say xi of root 2 comma root 3, the base field is q root 3 root 5. The conjugate isomorphism will not change any element within this. And this element is completely here, a constant here. So that is going to be, so you are not, if you are applying q root 2 minus q root 2, xi root 2 comma minus root 2, it is not going to change any element from here. And this is an element right here. So it is not going to change. It's exactly like this. But when you consider this one, this is going to change here. So this is going to be minus root 3 plus 2 root 5. We will do one more of a slightly different type. Let us say we want to find out psi of root 2 comma minus root 2 of psi of root 5 comma minus root 5 of root 2 plus root 30. So what is this? This is actually equal to psi of root 2 comma minus root 2. I'm going to expand this one. So I'm not going to evaluate our root 5. So minus root 5 of root 2 plus, see, we are going to use root 5 minus root 5. So take this root 5 out and we'll make it as root 6. This is not going to change because this is a constant element of this base field of this. 0, 5, so psi of 5 minus 5, its domain is q root 2 root 3. So root 2 is not going to change here. It is inside here. It is fixed. The only part which is going to change is here. This is actually 2 and 3 and that is also inside here. So this is going to be psi of root 2 comma minus root 2 of root 2 minus root 5 times root 6. This is going to change to minus root 5. Now this is equal to psi of root 2 comma minus root 2. I'm going to write it as root 2 minus root 5 times root 2 times root 3. So what is this? This is going to be this, the image of root 2 is minus root 2 and image of this one, these two elements are constant for this isomorphism. The only thing is this is going to be changing. So this is plus root 30. Or if you want to write one more step here, it will be root 5. Actually here I will be having minus root 5 times minus root 2 times root 3. And that is going to be minus root 3 minus root 2 plus